So, we will continue with our examples of the use of shell momentum balance and how it can be effectively used for solution of simple problems. Simple problems, I mean, in which the geometry is straightforward, the flow is mostly one dimensional and it is a steady flow. So, for all these cases we have typically solved two problems. I would like you to work with me on one more problem, and then I will give you some problems to work on your own, and I will provide you with the answers. But towards the end of this part, you yourself would start to realize that a simple shell balance approach would not suffice anymore. The geometries are getting complicated, the flow may have more than may have multidimensional effects. So, a generalized approach is necessary. But to get to that point, we will first try to solve a problem which is very simple, in which case there are two parallel plates and one of them is moving, the other is stationary. So, as the top plate, let us say the top plate starts to move, it would try to drag the liquid which is in between in the intervening space. So, as the top plate moves over the liquid, it will try to drag the liquid in between the two plates. So, a flow starts to establish, and we will look at that flow when a steady state has reached. So, the top plate is moving with some velocity, it imparts a velocity in the fluid in the liquid in here, and we are looking at this steady state. But just to make it more interesting, what we are going to do is we are going to assume that there exists a pressure gradient as well. So, the motion in the intervening space between the two plates, one moving, the other stationary, is caused by two factors. One is the movement of the top plate, and the second is the pressure gradient that exists in between 2 points. Now, if the pressure decreases in the direction of the top plate motion, if it decreases, then the fluid is going to have an additional flow due to pressure gradient from, let us say, left to right. So, the top plate is moving from left to right, the pressure gradient is in such a way that it would try to push the liquid from left to right. When that happens, we will say that it is a favorable pressure gradient. So, in order for a favorable pressure gradient, the pressure has to decrease as we move along in the actual direction. If it is opposite, that means if I move in this direction, the pressure increases, we will call it as an unfavorable pressure gradient. But the problem that we are going to deal with is flow between two parallel plates, one plate is in motion and there is a favorable pressure gradient. So, this is the problem which we would like to solve using shell momentum balance, and then there are several interesting offshoots of this problem which we will see as we move along. But right now, let us draw the picture of the two plates, one stationary, one is in motion, and see what happens to the liquid in between. So, this is my stationary plate, and there is a top plate which moves towards the right with a constant velocity equal to u, and let us assume that the gap in between these two plates is equal to b. In this direction it is x and here it is y, and the liquid flows in this direction. So, the upper plate end, there is a pressure gradient, I call it as dp dx, which is equal to minus a, where a is simply a constant. So, as we move in this direction, the pressure decreases. So, the top plate moves, it drags the fluid, and also I have a pressure gradient that forces the fluid to move from left to right. Now, here I again have to find a shell, draw a shell and make the balances. The flow is in this direction, but as I can see, the flow changes in the y direction. The principal direction of motion is x, but its velocity is changing with y. So, of course, my shell is going to have a thickness of delta y in here. Okay. So, the area of this, let us say the area of this is A. So, the shear stress tau is going to have two subscripts, principal direction of motion and the direction in which the momentum gets transported. So, it is going to be tau y x, x being the direction of motion and y is the direction in which the momentum gets transported due to viscosity, and this acts on an area A. So, this is the time rate of momentum in through the bottom face, which is located at y, and the time rate of momentum out would again be the same expression, but evaluated at y plus delta y. Okay. So, these are the rates of momentum in and out. Obviously, the convective momentum in and the convective momentum out need not be written here, since Vx is a function of y, Vx is not a function of x. So, whatever be the value of velocity at this point would be equal to the velocity of this point, and since it is an incompressible fluid, there would not be any accumulation of mass inside the control volume, and the convective momentum in, rate of convective momentum in would be equal and opposite to the rate of convective momentum out. So, those two terms will cancel, and that is why I did not write them in here. So, this is the molecular transport of momentum, viscous transport of momentum, which I have written, one is at y and the other is at y plus delta y. Again, since the system is horizontal, there is no question of having any component of gravity in the direction of flow. So, and the gravity is acting in a direction perpendicular to that of the flow. So, there would not be any gravity force acting over here. On the other hand, the pressure is going to play a role over here. So, the pressure at, let us say, at this point is P0, which is acting on an area with W and thickness delta y. So, that is the pressure which is acting on over this surface, and the pressure which is acting over this surface is minus PL times W delta y, and at steady state the sum of all this must be equal to 0. So, molecular rate of molecular momentum in, viscous momentum in minus viscous momentum out, no convection terms, no gravity term, no body force term, the pressure term, the force due to pressure, at steady state the sum of this is going to be equal to 0. So, again we divide both sides by delta y, take in the limit when delta y approaches 0. So, what I would get out of these two terms is dy of tau y x with a minus sign, and essentially this area is nothing but W times L, where L is the length of the control volume. So, W cancels from both sides, the L is remaining, which is being brought on the denominator. So, once you do that and once you substitute tau y x, so essentially what you would get is minus d dy of tau y x is delta p by L, and when you substitute and do the Newtonian fluid, what you get is d2 Vx by dy square is 1 by mu dp dx. That is the governing equation for this case. Pressure gradient, viscous transport of momentum, no convection, no gravity. So, once you integrate it, it would simply be equals 1 by 2 mu the pressure gradient, and then I have the y square plus C1y plus C2. So, that is the form of the velocity distribution, and I need two boundary conditions to evaluate them. One is obviously at y equals 0, no slip condition, that is y equals 0 is over here, Vx would be equal to 0, and if you use that, it would simply tell you that C2 equals 0. The other condition is y equals b is over here, and y equals b, Vx must be equal to the velocity of the top plate, and this would give you the expression for C1 as 1 by B u minus 1 by 2 mu dp dx times b square. So, I am using no slip at the bottom and no slip at the top, no relative velocity, no relative velocity at the bottom and at the top, and evaluate the constant C1 and C2. So, if we substitute this in here, the final expression for velocity for a flow induced by the motion of the top plate, also sustained by the presence of pressure gradient, would simply be equal to this. The expression would be, you should try to do it on your own. It is a very straightforward case, and this is what you would get. Now, this combined expression is very interesting, because it can be used to get some ideas about what kind of a flow would you expect if you just have the motion of the top plate and do not have a pressure gradient. If you look at the expression over here, if you look at this expression, if I say that there is no imposed pressure gradient, this is going to be equal to 0, and if that is equal to 0, Vx would simply be u by b into y, and the profile of the velocity in this case would simply be equal to, if this is y by b equals 0 and this point is y by b is equal to 1, the velocity would simply be like this. It is a linear velocity starting at 0 and the velocity is going to be equal to 1. So, this kind of a flow which is sustained by the presence of because of the motion of one of the, let us say, the top plate, no pressure gradient, no gravity, where the velocity profile is going to be linear, is known as the Couette flow. The Couette flow is quite common. The Couette flow is quite common in several industrial applications, where the motion of one plate sustains or creates a condition in which the flow takes place. And if you look at the second part of it, let us say your top plate is stationary. The top plate is stationary, the bottom plate is also stationary, but there is a pressure gradient which is imposed in between the two. If that is the case, then this part is going to be equal to 0, this is going to be non-zero, and this is the case, this would be the profile when the pressure gradient is when the flow is due to pressure gradient only. Now, what would it look like? I'll go slightly more deeper into this, because it would clarify many of the concepts. So, this is y by b equals 0 and this is y by b equals 1, and I am drawing the profile of the velocity when dp dx is 0. That means, when there is no applied pressure gradient, I simply get a linear distribution. Now, if I apply a pressure gradient in this case, let us assume that the pressure on this side is more than the pressure on this side, what we call as a favorable pressure gradient. So, as we move in the x direction, the pressure gradient progressively decreases, or in other words, dp dx is less than 0. So, if dp dx is less than 0, that is called a favorable pressure gradient, and you would get the pressure, the condition is probably going to be something like this. So, you have a pressure, this case is when we have a favorable pressure gradient and the top plate is moving with some velocity. So, this situation is unique, because there is a departure from the straight line behavior of the velocity, and it tries to closely resemble the second part of it. So, it is superimposition of the Couette flow over the pressure driven flow when the pressure gradient is going to be equal, going to be negative. That means favorable pressure gradient. It can also happen that the pressure on this side is going to be more than the pressure on this side, or the case of an unfavorable pressure gradient. If it is an unfavorable pressure gradient, then the profile would look something like this, So, this is dp dx is positive. That means, as I move from this side to this side, the pressure increases. So, therefore, the pressure is positive, the pressure gradient is positive, and it is the unfavorable pressure gradient. So, on the one hand you have Couette flow, where you have get a linear distribution, favorable pressure gradient and unfavorable pressure gradient. There is one more interesting thing to see here is, in Couette flow the maximum takes place at y equals b, but if you have an unfavorable pressure gradient or a favorable pressure gradient, the location of the maximum velocity could be different. It is not going to be at y equals b, it could be at some point in between y equals b and y equals 0. So, if someone tells you that try to what is the location of this maximum velocity, so you would like to find out what is V max, what is the location of the V max, and we understand for V max this dvx by dy must be equal to 0. So, in order to get V max, the dvx by dy would be equal to 0, and when you substitute the expression of Vx in here, differentiate it with respect to y and make it equal to 0, what you get is this y, I call it as ym. So, this is the maximum, this is the location of y at which u becomes um. So, this is the is the maximum velocity and ym is the location of the maximum velocity. So, when you simplify, you would simply get ym to be equals b by 2 1 plus 2 mu u by a b square, where a I have defined simply as minus dp dx. So, you can you now have seen that what is the location of the V max, what is the location of the V max, which depends on the pressure gradient, which depends on what is the top plate velocity, which depends the geometry, the separation between the top two plates, and the thermophysical property, the transport property, which is mu. So, the V max will not lie over here, V max will lie somewhere in between these two. That is one more interesting thing that one can see from here is, let us again draw this Couette flow diagram, where we have two plates, no pressure gradient, linear distribution, negative pressure gradient and Couette flow both are acting in the same direction, unfavorable pressure gradient, but the pressure gradient is trying to force it from right to left, Couette flow tries to drag it from left to right. So, you should be able to find out what is the negative pressure gradient. Suppose it is asked that what is the pressure gradient that needs to be imposed such that there is no net flow. So, what you see here is for this case. So, I am drawing the case for Couette flow and the flow when I have the negative pressure gradient. So, if you see here, partly the flow is in this direction, in here the flow is from left to right. So, this is a unique case where the pressure gradient is unfavorable, that means dp dx is positive, and you have towards the bottom the liquid is flowing in this direction, towards the top due to the Couette flow the fluid is moving in the right direction. So, if someone asks you what should be the relation between u and dp dx, that would give you 0 net flow, that is q equals 0. I need to find out the relation between the velocity of the top plate and the imposed pressure gradient such that there would be net flow rate to be equal to 0. So, this is really an interesting thing to see, and as I have drawn here, the flow towards the bottom is going to be in this direction, towards the top it is going to be in this direction. But in order for Q to be 0, the net flow to be 0, the algebraic sum of the flow rate here and here must be equal and opposite. Okay. So, the area under this curve and the area under this curve must be equal. So, you would be able to find out what is, in order to do that, what if Q is 0, this essentially tells you that the average velocity for this case must be equal to 0. So, the average velocity for a situation in which dp dx is positive and this is moving with velocity, the Couette flow is towards from left to right, the average velocity must be equal to 0. So, one can find out the expression for average velocity, because the expression for velocity is known to us, the expression for velocity is known to us. From there I need to find out what is Vx and equate this Vx to be equal to 0, which implies that Q equals 0, and this should give me a relation between u and dp dx. Okay. I will leave that for you to work on, but in order to obtain this Vx, I need to integrate. So, this V must be equal to the area, which is the flow area, and the flow area is going to be Vx times whatever be the width times dx, and x varies between 0 to b. So, this is going to be w, where w is the depth of this. So, this is going to be your average velocity. If you equate this to be 0, you get the relation between u and dp dx. So, an unfavorable pressure gradient can give rise to a situation in which the net flow rate is 0. So, that is one more the same problem gives you another interesting way to look at the same problem. The third part of this specific problem can also be thought of to provide a different type of a problem. Let us say that the top plate is moving, the bottom plate is stationary, you have a favorable pressure gradient. So, initially it was a straight line Couette flow, and then when you start applying a favorable pressure gradient, the flow starts to deviate from its straight nature. Okay. When the applied pressure gradient is large, then you simply have the pressure gradient that way I have drawn it previously, Couette flow when you have dp dx to be negative. This is u with moving with u. So, this is the case where dp dx is equal to 0. So, now we are trying to compare between no pressure gradient dp dx to be equal to 0 and a pressure gradient which is favorable, that is dp dx is negative. The maximum is here. In the previous case, the maximum was here. Now, if you progressively reduce the value of the applied pressure gradient, the profile would look something like this, and this is the location of the Vmax, and a point, and if you reduce it significantly, then it is not a straight line. So, it is not a straight line, but this remains the location of the maximum velocity. So, the maximum velocity starts to move in this direction, starts to move from right to left, and when it is dp dx is 0, it is over here, but when dp dx is not 0, but small, then also you get the maximum velocity over here. So, for some value of dp dx, so that means if dp dx is large, your Vmax is not u, Vmax is something more than u. dp dx is 0, your Vmax is equal to u, that is over here. But when dp dx is small, it may be possible that Vmax is still equal to u, which is this case. dpdx is small, but you still have the Vmax at the top. So, what is the limiting value of dpdx? Can you find out the limiting value of dpdx such that Vmax would still be equal to u? So, it is no longer a straight line, it deviates from a straight line, it is no longer a straight line, but the maximum is still over here. So, what is the condition that one has to make, one has to impose in order to obtain the limiting value of Vmax such that your Vmax limiting value of dpdx such that the Vmax is still equal to u. I would leave that problem for you to think about. I will just give you a pointer that how would the profile look like when you have this is my straight line, the velocity is equal to u, and this is the limiting case. This is the limiting case where the maximum velocity dpdx is negative, this is dpdx is negative, but the maximum is still over here. Any increase in dpdx and what you are going to get is the maximum is going to be somewhere here and not the value of u max. So, this is your dpdx limiting. So, what is how do you find out what is the value of dpdx negative? Look at the profile over here. If I expand this, the limiting value can be obtained by looking at the profile. That means, the slope of the curve when it reaches the top is going to be equal to 0, or in other words dvx dy at y equals b is 0 for the limiting case. Is that clear now? I have a linear profile and this is the case when dpdx is large. I progressively slowly start to reduce the value of dpdx. If it is too small, then it is no longer linear, but the maximum is still over here. If it is large, it is not linear, but the maximum is not over here. So, this is the limiting case which is at the junction where the maximum velocity is over here, and any slight increase in dpdx tilts it from left to right and you get a new maximum. So, how does it look like for the limiting case? It simply approaches the wall with a 0 slope. If it approaches the wall with a 0 slope, then this is the condition which you can use to obtain what is the expression for dpdx limiting. This is something which I think you should do it on your own, and it would give you a very interesting result. I will just point out a feature of this problem of this limiting dpdx. It can be asked, like, in order to move the plate, top plate, you need to pull it, you need to apply some force in order to allow it to move at a constant velocity over a film of liquid, over a film of liquid which has a finite depth. What would be the force which needs to be applied when you pull the top plate? What is the force needed at the limiting condition, limiting dpdx, the one that we have just described? So, the limiting dpdx, what we define as the value of the pressure gradient. If you go beyond that, the maximum of fluid velocity will not lie at the top plate. It would be somewhere in between the top plate and the bottom plate. But dpdx limiting is that value which is the maximum pressure gradient that you can apply while maintaining the velocity at maximum at the top plate. And we have seen how would the profile look like. So, looking at the profile, I think would give you a pointer about what is the force needed to pull the plate in that case. if you see, the force is simply the viscous forces. The viscous force is given as mu times the velocity gradient. Now, if you look at the profile that we have drawn over here, the value of dvx dy is equal to 0 for under the limiting condition. So, if this value is equal to 0 under the limiting condition, then what you get is an interesting result, that under this limiting pressure gradient, you do not need any force to sustain the motion of the top plate. So, the top plate would perpetually move if you can maintain the limiting condition as it is. So, it is an interesting problem, that the one that we have described or discussed. First of all, it gives you an idea of Couette flow. Only the motion of a plate can drag fluid, which is known as Couette flow. You can also impose a pressure difference, either assisting the flow, Couette flow, or opposing the Couette flow, and in both cases you get the profiles. In the case where the pressure gradient is opposing the Couette flow, then near the plate, top plate, the fluid will still be moving towards the right. Near the bottom plate, because of the pressure gradient, the flow will be towards the left, maintaining the no slip condition at the bottom plate. And a condition, you can think of a condition in which you have an opposing pressure gradient, Couette flow towards the right. The combination is such that there would be 0 net flow. The trick to do that problem is to find out what is the average velocity, cross sectional average velocity, equate it to 0, and you get what is the opposing pressure that you need to apply in order to obtain a 0 net flow. And the last part of the problem, what we have seen is that the maximum in Couette flow, the maximum velocity in Couette flow will always be at the top plate, which is moving with some velocity. If you start applying a favorable pressure gradient, the linear nature of the curve will start to deviate. If you apply too high a pressure gradient, then the maxima is not going to be somewhere in between the top plate and the bottom plate. But if you apply just the right pressure, there would be a maximum pressure gradient in which the velocity maxima will still be at the top plate. Any slight increase and the location of the maxima will come down. That is what we call as the limiting pressure gradient. And under that limiting pressure gradient condition, there would be no force required to pull the plate over the film. So, a single problem would clarify many of the concepts of pressure gradient, flow, no slip condition, no net flow, and so on. What I would do in the next class is to give you some of the problems to work on. So, I will introduce the problem, explain a bit of it, and provide you with the answer, and I would expect you to do it on your own and come up and check with the solutions.